Okay, we have time for quick comment and question. No? Okay, thank you. Let's move on to next talk. So next talk is invited talk will be given by the Pepe Jin. He talk about the toward understanding a linear complexity and change. Please.
Okay. Thank you for inviting me to give this talk, and I try to use this short time to convince 3 ideas, probably too ambitious, but let's try. Well, we heard a lot about different type of El Niños, Central Pacific El Nino or Eastern Pacific El Niños, and I think it's seeming to converge in this morning. Lots of people are talking about the excitations or so on and so forth about that. However, there is a question whether there is a theoretical understanding why we would have, or why we should have, or could have 2 types of El Nino. And I want to show this result, which I think some of them, if you were here last year, may have heard about that. That is that I have been seeing these 2 leading modes out of the coupled system from like Zebia-Chem type of model. When you analyze that either analytically or numerically, you always find not 1 but 2 are coming out of the continuum of ocean modes, which is heavily damped. But the patterns of these 2 modes, leading modes of the system, which I noted early on and later in my paper, which about recharge oscillators, actually the part 2 was not well read, but in the part 2 I have shown there are 2 modes. One is related to the wave delay oscillator, one is the recharge oscillator. The 2 modes can both exist. However, the patterns of that paper was not distinguished. So later, a student come by to analyze ZC model. So this ZC model results the eigensolutions, the leading eigensolutions, the linearized solutions. You see, we called, at that time, we called a QQ model. It had a period about 4 years, and patterns centered in the more the Eastern Pacific. There is another mode which also coexistence slightly less, the growth rate slightly weaker, but the period is not about 2 years, and ST is nearly more close to Central Pacific. So these 2 modes were there. We know that for some time, but only lately I think it become the connection because we realize now there is observational correspondence, so-called Eastern Pacific and Central Pacific. But what is the mechanism or what is the physics behind these 2 modes? One thing you can do with simple model, you can change parameters. One parameter we change is so-called reduced gravity in the Zebia model, which controls the Kelvin speed propagation. So if reduced gravity is larger, then the speed will be larger. So if the speed is larger, 1 is a standard value. If you reduce increase 50%, there's 1 mode, this QV mode or the Central Pacific mode, actually period become 1/2 as expected. If your time scale is faster, then the delay time scale will be shorter and the period will be shorter. As you reduce the 1 standard value by half, the period of that oscillator can become 4 years. It is almost linearly followed parameter, where the other mode, which is called recharge mode, actually doesn't change as it was analytically formulated. It should not depend on speed of the propagation. So there are 2 modes which we know before, but now by distinguishing it in terms of dependence of the physics, we can really now tell they are really 2 different oscillators operating in simple frameworks like ZC model. But I suppose those physics are not, I think, a approximation of what happens in the nature. So I think it is arguable that at the current time state on the stand parameters, we might have 2 modes of different frequencies. So I want to summarize quickly because I want to talk about another idea. I think this is one of the idea directions we can understand this complexity in terms of 2 types of El Nino. But the reason I think the understanding of the basics is actually there. We have recharge oscillator paradigm and wave delay oscillator paradigm, which we often thought this kind of one, but actually I want to show here, maybe they can be interpreted in 2 different types of El Niños or 2 modes of El Niños. And of course, different excitations, as we see in this morning, may excite them differently. So it depends on changes of things or noises, which we not quite understand, but can really excite it differently. Well, I want to talk about another idea of complex, make the El Nino a little more complicated. That is, El Nino is happening, but we also have a well-known annual cycle. Earlier days, 20 years ago, we look at the annual cycle in the cold town region, interacts with El Nino, but the annual cycle there is relatively symmetric on the equator. Equatorial annual cycle is symmetric, so it's not going to change El Nino, create new patterns. Now, if you look at El Nino in the Eastern Pacific, which comes every, let's say, 4 years, make it simple, we also have the warm pool follow the sun. Summer will be in the north, and the winter go to south. When these two SRT and variation superimposed together linearly, it will create actual warm SRTs, or in other words, warm pool in the winter time when El Nino comes will further extend to the east on the south side of the equator, or creating so-called zonal SRT, zonal ITCD events in the south, when G. was calling that. What it happens is that convections have a threshold a dependence on temperature. If the temperature warm together exceeding 27 or 28 degrees, then it creates more convections, to create actual convections here off the equator. If you, that's in the El Nino like winter. But then this actual heating precipitation could create a subsidence, which create a symmetrical response on the Philippine Sea, will be reduced precipitation. This pattern is associated with El Nino, but it also has to associate with nonlinear interaction with warm pool migration annually. And because of that, the time scale of that pattern will be very different from the El Nino, also different from the annual. So, and you can analyze that, use so-called UF analysis. This was work done by my student, actually co-supervised by Axel Timmerman and myself. And if you look at first the UF, the equatorial winds, of course, that will be the El Nino winds, and the time scale, time variation of that wind pattern will be almost identical to Nino 3.4. The first PC, the correlation with Nino 3.4, is going to be like 0.95 or something like that. So let's call this the El Nino associated winds. But you have another pattern, second UF, which is anticyclone, so-called Philippine anticyclone. Then there's a cyclonic motion in south of the equator, so it's antisymmetric. And the time series is very different. It's associated with El Nino, but the scale is very different. The black line is the time series, and the red line, which I covered that, yellow line, which I covered that, is actually a time series, use let's say El Nino time series, Nino 3.4, first the PC, multiplied by this warm pool migration, the annual cycle, cosine omega t. Omega A stands for the annual frequency, precisely annual. And you multiply them together, this indicating that's a non-linearly interacting, they almost recover, it almost recover the time series. In other words, we do have this non-linear interaction of El Nino warm pool creating this, we call it El Nino C mode, El Nino combination mode. Now, that was actually, this kind of behavior it's very simple. If you have two violins playing in this room with two different tones, and if your ear is very good and you are good musically good, you might hear a third tone, which is called Tartini tone, because the two sounds not linearly add together or interfere. You can see the linear composition, but also the two sounds, when hit your eardrum, create a nonlinear reaction, which is actually create a combination tone. And that is a very, this is in the music and known for 300 years. It's very simple. Two cosine function multiply together, the frequencies will be add and multiply. But this here is, as it happened, the El Nino phase, this is a typical El Nino composite El Nino phase. The response of this Philippine anticyclone is, during the one phase, it has changed sign. The period is much shorter, it's around 15 to 8 months. And of course, this is this theoretical prediction use annual cycle and the El Nino. You can really capture the yellow is the theoretical prediction, the black solid line is the observed one. And of course, this is due to this Tartini tone thing. So let me summarize the second point. El Nino is a little bit more complicated by the fact that it interacts with annual cycles such as warm pool annual cycle. And this is important. It is actually deterministic in the sense, if the El Nino is known, then this signal is well known. It's completely determined, almost completely determined, I would say. And, but it has a much richer time-space expression now. It has anti-symmetrical component come into, and the frequency is around 8 to 15 months, which tend to disrupt the monsoon progression very effectively, which I cannot talk about it at the moment because I want to talk about the third idea, which was my time. But okay, I will try to talk quickly. Well, the third idea is that El Nino does interact with noise. And if you look at 97, there are lots of talks about the western wind birds kick off El Nino. If you do a monthly average, then you have to see this slower kind of western winds, which is not really quite related to the Acetina in Central Pacific. It's there to kick off or start the El Nino. So this is, has been now, I mean, this morning you heard lots of this excitation thing. So how do we look at that? Well, this happens during the El Nino more in the La Nina, so it is phase-dependent or state-dependent kind of noise. Is state-dependent. You can put this kind of state-dependent noise heuristically into a very simple recharge oscillator model. Then you can analyze this theoretically that the state dependency, if the no state dependency P is 0. If the noise does depend on state, so in other words, it's multiplicative, and let's measure it as so-called B parameter. You can prove that very easily, that the skewness and also the big events, also called, because with this skewness, the big El Nino events can happen. La Nina events normally not as big, so let's count the big El Nino events. And the skewness are both proportional to this parameter linearly, almost linearly. You can analytically derive that in a very simple model. But does that hold in the reality, where you can examine the so-called, look at the residual noises and then look at the state dependence and find the B parameter in the models? They here use control runs, many of models, and scenario runs, and some observation or Liana's data, put them all together. They tend to follow the same way, more or less, of course, have lots of scat. And the super El Nino events, which is more than 2 standard deviation above in terms of comparing standard deviation. And you can see the different models, the skewness and the super events are really related very well. So this simple prediction seems to, a simple theory seems to work, to be working. How that relate to what happens, okay, I'll try to be quickly. In the listened data, well, we found that, as we heard a lot in the morning, there is a triggering mechanism from the north called whatever Pacific Mediana mode, so I called this a punch from north. And then there is this year there is a paper saying there is a punch from south, and you look at these 2 factors, but you do need to consider whether initially the warm pool is well charged. You need to look at the earlier, like the year before, then how entire warm pool evolution of quite a few months as an indicator of warm pool slow charging and charge state. If you look at these 3 factors, then the 3 large events what we observed in good data, all these 3 factors stand out, while the other El Ninos, at least 1 or 2 are not very good. This year, early on, actually, if you measure heat content that way, the heat content, what we see, is actually just a Kelvin wave, but the whole warm pool is not really well charged, where there's no southern booster. The northern hemisphere seems to be kicking it. So this year, this November, maybe this is handcuffs, of course. It's after the matter of fact, we can understand this a little better now, why we wouldn't have alarmed early on about the super El Nino coming. But anyway, in theory, state-dependent noise really can trigger strong El Nino events, although it's not predictable due to a noise-induced ability. In reality, probably we need to check the triggering, or so-called these slow noises, carefully. They come from either north and south, maybe from east or west as well. But I want to conclude my talk. Thank you.
Okay, thank you for a great talk. Okay, so we have time for comment, 1 comment or question. Any comment or yeah.
Early this year, people really thought there's going to be an ENSO event, and it's not. Can you give us any insight on why it's not?
Okay. I think early on in the March, if you are hearing McFadden's talk, clearly early on in the March, there was a Kelvin waves excited by west wind bursts create a lot of heat content on the equator. However, we have to look at the warm pool the warm pool heat content had to be slowly charged, and that can evolve to, that slowly charged is important because this ENSO, we are looking at a slower oscillator. So a Kelvin wave, quick Kelvin pulse is not enough to contribute to this, kick towards the El Nino. So that's one. But also you need some forcings from, in addition to the initial condition forcings. And that's two factors we are looking. We have the northern punch, but we don't have the southern booster. So I think this is probably what's happening in this year, but every El Nino is different. So I think there will be much more discussion down the road for this El Nino because this alarming, the Kelvin wave coming and alerting us to thinking about El Nino. I think this thinking needed to be really, I think, revised in the sense of thinking about a slower component rather than a fast one. Okay.
Okay, thank you, Pepe.